Okay, so let's start. So I put up this slide to talk about the origin of the word mathematics. Mathematics comes from a Greek word, which means that which is learned, or what one gets to know. So mathematics is really about study. Okay, if you don't like study, maybe you don't like maths. It's only when until the Aristotle time they define this word to be arithmetic or geometry. But really, mathematics is about study. Yes. So the desire to know, the desire to study, okay, is important for you to study mathematics. Otherwise, you really feel tired. It's a desire to study, to know. And this is also the spirit of science. Science means you want to know. If you don't want to know, I talk to you so much, also no use. Okay, because you don't want to know. But if you want to know, you dig even more and more without me telling you. It's a desire to know, a desire to study. And if you want to do well in maths, it's not you are good at it or not. It's just about you want or you do not want to know. Everyone will have their weakness, but some desire, everyone has the same desire. Yeah. Okay. Okay. Let's start from the definition of concept. Okay, be careful when I say the word definition. Please see what is the thing I want to define. Okay, then store in your memory for short memory at least. Okay, so what's the concept? So a left concept. So before a left concept, what do you need? Need a subgroup. Okay, so a left concept. Of a subgroup H in G is the set. What set is this? CH, okay, call it CH. CH equals to C times H, where H is in a subgroup H. So where does this C come from? G, okay. So it's the set that so this C have to come from. So that's it. Let's C and G. Or for all C. Okay. So is this a subgroup or not? Huh? This is generally not a subgroup. What's the picture? What's the example you should keep in your mind? What's the picture you want to keep in your mind? What's the simple group that you can think of? You need until this now is already 5th week, right? 5th week. So you must have at least some group inside your mind. For example, symmetric group, integer modulo n, and real number, rational numbers. Okay. Let's say I take G to be Z3. So what are the cosets here? What are the cosets here? Hmm? What are the cosets here? The example we left last time. What's the coset inside here? Yep. So 0, 1, 2. So in this case here, I see 0 as the trivial subgroup. 0 is a trivial subgroup of Z3. Okay. And then what are the other elements in Z3? 1 and 2. Okay, so we can add 1 and 2 to my trivial subgroup, where I get 1, 2. Okay. So this is a set, right? So really, I cannot just write like this. Really, I should write them as set. Okay. Yeah. So I need to at least keep one example in your mind. So in this example, this coset partition my group. Yeah, partition. Still remember what's the definition of partition or not? What's the definition? What's the definition of partition? Hmm? What's the definition of partition? So every word mentioned from the maths lecturer, right? It must be defined. Okay. So you must know the definition of every word the lecturer is talking about. Okay. Otherwise, you definitely confuse. Okay. So what's the meaning of that partition? Same equivalence relation. What's the definition of partition? So what's the idea of partition first? Uh, yeah, good. Okay, one by one. So, uh, so you said that there's some similarity between object, okay, so that you can group together. But this is not the first definition of partition. Okay, so the first definition of partition is just I have a set, say A. Okay, I split it into finite number of sets. Okay. Then I demand that between AI, there's no intersection. Disjoint union of set. This is the definition of partition. Okay. So we will say of set AI partitions a set A if first A can be written as a union of AI. Second, AI intercept AJ is empty for all I not equal to J. Okay, in other words, is this expression here. Okay, so you see, so to talk about maths, right, you need to be able to write it in maths, call it in English. Okay, so the first two part here is the English part. Okay, A can be written as the union of AI, AJ intersection is empty. Okay, so to write it out mathematically, this is done by the last equation. Okay, you need to do both. You need to be able to do both. You need to be able to say in English, write in mathematics. Yeah, so, but still it's true that these AI have some relation. This is actually a proposition. What's that proposition? So given an equivalence relation, you can get a partition. Given a partition, you can define an equivalence relation. Okay, so this is a proposition you should have proven before, or at least you have seen before. Okay, if you haven't, so if you want to refresh your memory, you can go back to Artin. There's a chapter on the equivalence relation. You can read about it because I won't go into the chapter equivalence classes relation again. Okay, so you can go to that subtopic and read about it. It's also in the chapter of groups. Okay, so what's the proposition? Equivalence So I don't write out the statement, but given any equivalent classes, you can get your partition. Given any partition, you can define a equivalence relation. Okay. Okay. So what's the natural way to get a subgroup in this case? So we need a subgroup to define coset, right? Where is the source of subgroup? Do you remember? Where's the natural source for subgroup? Identity? They want just define a trivial subgroup. Yeah, source mean how say it? It's like what's the source? Source. Where is the natural place you can look for subgroup? Kernel. Okay. The kernel of a homomorphism is a subgroup. Okay. So let's say we have G and G prime. And there's a homomorphism phi. So kernel become a subgroup. Okay. In particular, this subgroup map to 0 in the image. Okay. So since this is a subgroup, right, we can form a coset of it. Right? We can form the coset of it. So let's call my kernel phi f h, and then we can form a few cosets. So these are not subgroup. Maybe I draw something like a cloud. Okay, we have this coset. Yeah. So where should this coset go? Okay, so for example, where should AH go? Or where should BH go, for example? BH should go to where? After you apply phi. Okay, when I say this, I don't want you just to think about it. I want you to work hands-on. When I say apply, you should go and apply it. Okay, your brain should think, what is phi BH? Go and apply it. Okay, what do you get? Phi B. Why? Why just phi B? Okay, so because phi is a homomorphism, so phi B H can be equal to phi B on phi H, which is just phi B, because phi of all the H you get identity. H is a kernel. Okay, so be careful when you write about these things. Don't treat H and B as the same thing, right? So H here is a set. Okay, H here is a set. So what you are really doing is, for all C in H, phi B C equal to phi B times phi C. Okay, and let me move to the back. Phi B times phi C, and then phi C is just identity, which is equal to phi. Since this is true for all C, okay, so I can write it in this H form. Okay, okay. So be careful when you write these things. Okay, because homomorphism really only defined on elements, not on set. Okay, so why I write set? Because no matter what C I put in this expression, I will get the same answer. Okay, so here is an element times set. Phi B times phi H is also an element times set. So actually, what is this? This is a set equalities here. And then here, yeah. So this one is less precise. Okay. So what's precise here is the second line here. Okay. This is what I really mean. Okay. So really, I cannot put this actually as precise. Okay. Or maybe I say that. Okay. Yeah. So BH gets sent to VB. So similarly, you'll see that. How about the rest? Maybe AH gets sent to V. Then CH gets sent to AC. Okay. Yeah. So you can see that different concept get sent to different things. So let's prove this. Yeah, let's prove this. Okay. Let phi to be a homomorphism And let's take two arbitrary element in G, okay? And then we fix our kernel. Let's call it K in this case. Okay, kernel, K for kernel. Then the followings are equivalent. First, Vx equal to Vy implies x inverse y is in K. Okay, maybe I write it bigger. And then y is in the coset of xk. And for the coset yk and xk is equal. Okay. So do you guys know what is a TFAE is? Yes, the following are equivalent. So how to prove this kind of statement? Okay, so one thing you can do is you show that 1 to 2, 2 to 3, 3 to 4, and then 4 back to 1, so that they all implies each other. Okay, but also of course you can try other way. For example, 1 if and only if 2, 2 if and only if 3, 3 if and only if 4. Okay, so how to go from 4 to 1? So you just go from 4 to 3 to 3 to 2, 2 to 1. Okay, so you need to establish a link between each of them. Okay, depend on what you want, how you do. Okay, you must form a closed loop. Okay. So what can we do? So maybe we can do the first strategy. Okay, so these proofs are not too hard, so we will quickly go through it. So how to prove from 1 to 2? Okay, we know that Vx equal to Vy. We want to show that x inverse y is in the kernel. So what does it mean by x inverse y is in the kernel? What's the property of kernel? P of the element is equal to identity, right? Identity in G prime, good. But phi is a homomorphism, right? Okay. So this means phi x inverse py equals to identity. Okay. Make sense? Okay. But what? Phi is again a homomorphism on inverse. So you get phi x inverse py is identity. Okay. So what can you do? You can apply px on both sides. And this is the condition you have. So in this case here, we not only go up to down, right? We also go down to up because this implication is reversible. Okay. The operation in the groups is reversible. Okay. So actually we establish extra link here. So 1 if and only if 2. Okay. Any question? This one should be not too hard. So you should understand this. Okay, this is the basic argument using definition only. Okay, no construction at all. So if you have question, you should definitely ask now. Okay. Okay. Okay, next. Let's see if we can go from 2 to 3. Okay, we know that x inverse y is in K. Okay, meaning what? Meaning that exists an element in K such that X inverse Y equals to K. Real? Okay. Because it's in K, right? So in particular, it's one element in K. Let's call it small K. Okay. So what does this imply? This implies what? Yeah, multiply X on both sides. Okay, so you get Y equals to X K. What does this imply? You write Y in terms of X times an element in K. In particular, this means that Y is in the coset of XK. Okay. So these are all just by definition, and then play around with group property only. Okay. So here is the definition of coset. Okay, it's the thing we learned just now. Okay. Similarly, this argument can go backward or not? Can I go backward? If I X start with an element in the coset, can I return my element in this form? Then can I take inverse of X? And then if it is equal to K, then it is in K. So this argument actually works both ways. Okay, and establish another if and only if implication. Okay. Okay, next 3 to 4. Okay, let's start from 3. Okay, so suppose Y is in XK. So this means what? This means Y is equal to S little k for some K. Okay. Okay. So since I already written in this form, right? Since in this form, what can we do? So first of all, notice that this is an equality of set. Okay, so meaning you need to show inclusion, subset inclusion. Okay, so in this case here, you need to show YK is a subset of XK and XK is a subset of YK. The same as showing two numbers is equal. Okay, if you want to show that something is equal to a number, what do you have to show? You have to show that one number is greater or equal to that number. The other number is greater or equal to that number, so that they're equal. So this is the same here. Okay. Does it make sense? Okay. So let's start with one of them. So let's take V from YK. Okay. We want to show that it is in the coset XK. So meaning it can be written as X times something else, something K, right? So if I take V from YK, that means there's this, let's call it K1. Okay, maybe this is a bit longer, so we get more space here. So we take, there's a K1 such that V equals to YK1. Okay. But what do we know? We know things about Y. Okay, we know things about Y. So already from the condition here, we can write Y in terms of SK. So meaning V equals to XK times K1. Okay. Does this enough to tell me that V is in the coset SK or not? Here got SKK1. Right. Yeah, but K is a subgroup. Okay, K is a subgroup. So in particular, K1 is in K as well. Okay, so V is in, and V is equal to X of, let's call it K, K2, which is in XK, where K2 is just K times K1. Okay, how about the other direction? For the other direction, what do? You also take an element W in XK, okay? You want to show that W is also in YK, okay? So meaning you need to write W equals to Y times something in K. So since W is in XK, then W is equal to X times, maybe call it K10, or some K10 in K, okay? Can you write X as some thing in Y or not? Oh, yeah, we know that Y equals to SK. We also have X equals to Y K inverse, right? So this assumption here is a equality of elements in the group. Okay, so you can do group operation in particular. Okay, so you just multiply K inverse on both sides. Okay, to get the expression of X. Then it follows that W is equal to Y K inverse K10. Okay, is this in the coset of YK or not? Why? Why is it in the coset of YK? Because if K is in the subgroup, K inverse is also in the subgroup. K inverse is in the subgroup, K10 is in the subgroup. Subgroup is closed under multiplication, so K inverse K10 is in the subgroup of K. So it follows that W is also in the coset of K, Y. Okay. Okay. That's right. Following. Okay. So what does this mean? So have we finished yet? Okay, we haven't quite finished yet, right? So we only have one direction just now. So seems like we are closer to the second root just now. So how about we see if we can go back like this? So suppose we know that these two cosets are the same. Do we know that Y is in XK? So we just want to show Y is in SK, right? So let's try the other direction. So let's try to establish this direction. Since YK equals to XK, okay, so this is equality of set. So this means there exists K1, K2 such that YK1 equals to XK2, SK2. Okay, SK2. So YK1 equals to SK2. Yeah, so you see, one thing to note here is K1 not necessarily equal to K2. Okay. Is it okay? K1 not necessarily equal to K2. Because you just have equality of set. Okay, you can simply pick which K1 and K2 works. Okay, it doesn't need to equal the both or the choice of K. Okay, because it's just equal to set, some equality of set. Okay. It is just some k inside the set. You don't know which one. Maybe they are the same. Maybe they are different. When you go to the element. Okay, then what can you do? Yeah, inverse. So which inverse you want to take? So you multiply both sides by k1 inverse. Multiply k1 inverse on both sides. From the right. Okay. So in this case here, we also see that y is in xk because k is a subgroup. So k1 inverse exists. K2 times K1 inverse is also in the subgroup because it's closed under multiplication. Okay, and follow? Okay, yeah. So this is things that this is kind of the things you will be, I'll say, I'll test you in this course. Okay, some proof require construction. This kind of proof doesn't require construction. You just unfold every definition and then you will get the things you want. Okay. What do you mean by short section?
Maybe for subsection is this question have
I mean, depends. Depends, yeah. But the question in the exam will have something, some proof question, but these proof question just require you to unfold the definition to prove it. That's all, meaning you need to be very on top of your definition. And I allow you to bring cheat sheet. So you need to know how to use the definition. Okay. So in exam, I won't provide you definition. You can write it in your cheat sheet. Then the job for you is to use the definition. Okay. So if you want to practice, how to get practice? One source is do the tutorial I gave you. The other source is to look for the lecture notes that I posted for you. The Duolingo one. Duolingo have a lot of examples. And then I think I also posted previous year assignment or tutorial question, right? Yeah. Do those. Do it. Okay. If you want to practice, do it. Okay. Don't wait. Nobody will force you to do one. Okay. You have to work out yourself. And I'll be available office hours. Okay. Some of you even message me on Teams, right? I do reply. Okay. So please work it out yourself. Okay. Because you are an adult already, right? I don't want to like keep pushing you. Okay. So next. Proposition. Okay, again, proposition. So what are these concepts just now? So actually, like what we have mentioned before, this concept. Okay. So usually, right? Usually, we won't talk about left or right concept. So similarly, you can define what is a right concept. Okay. But when we talk about concept, we will say about left concept. Okay. In practice, we mean left concept. Later we will see how we compare left and right. They are not far different. Okay. Although they might get different things. Okay. We will see later. So the concept of H in G actually are equivalence classes. Okay. Just now we observed that in partition set, right? Okay, so it somehow come from a equivalence relation. Okay, what's the equivalence relation here? So A is equivalent to B if B is equal to AH or some H in H. Okay, so I claim that B equals to AH for some H in H is an equivalence relation. Okay, so to prove equivalence relation, what do you need? Three things you need. Does you remember or not? What are the three things you need to check in equivalence relation? Now remember, three things you need to check. First is the reflexivity, and then symmetric, and then transitivity. So what are these words? Okay, so you must remember what does it mean by equivalence. So this is a very important concept in mathematics. How do you say I and you are the same? Okay. Reflexivity, symmetric, and transitivity. So this really captures the equality of numbers. What does it mean by numbers? Okay, how to write down two numbers the same? Can I say 3 equals to can I say 3 is not equal to 3 or not? 3 must equal to 3, right? Because they are the same. If your equality doesn't give that, then something is wrong. Okay. How about symmetric? If 3 equal to 4, does it mean by 4 equal to 3? Okay. This is not always true. Okay, this is not always true. You are like take for granted from kindergarten, from primary school. You know that if 3 equals to 4, 4 equals to 3. But this is not always true. Okay, this is not always true. So we need to impose this. It has to be symmetric. Okay. How about transitivity? A equal to B, B equal to C. How about A and C? Is there a link or not? Okay, might not be a link, but we need to impose in my equivalence relation. Okay, so if I can go from A to B, B to C, then I can go from A to C. Okay, so do you want to quickly see why this is the equivalence relation? I leave out some word here. So these concepts are equivalence classes. So reflexivity. So why A is equal to A? Because you need to write A equals to A times something in H. So what's the thing you need to multiply with? A equals to A times identity. How about symmetric? If A is the same as B, is B the same as A or not? Huh? If A is the same as B, that means what? A is the same as B, then the equivalent say if the relation says what? A equals to B times some H. Let's go and H1. Can you write B as A times something or not? How? Then you multiply inverse on both sides. Inverse of what? H1 inverse on both sides. What do you get? You get A H1 inverse equals to B. Okay, so you write B as A times something. What is the thing you multiply with? H1 inverse. But this H has to be in the subgroup. Is H1 inverse in the subgroup? No? Yes, because H is a subgroup. Okay, and H1 is in the subgroup. The inverse is in the subgroup. So this means that B is in B equals to A H inverse in and also H1 inverse is in the sum. Okay, maybe I left you to do for this sensitivity. Show you also. Okay, so you need to do a few times. It's quite similar to the computation we did just now. So from here, from the proposition I gave you at the start of the class, so the corollary is the left coset of a subgroup of G, of a group G, partition the group. Okay, so you partition the group. Okay, so actually this corollary here, you already can see from this proposition. Okay, if they get sent to the same place, they really come from a same coset. Okay, so there's no non-trivial intersection. If you intersect, both of them have to be the same thing. Okay, there's no non-trivial intersection. If they intersect, they are actually the same coset. Okay, so if they intersect, they are the same coset. There's no non-trivial intersection. Okay. Yeah. Remember last time we said that we proved that intersection of two subgroups is still a subgroup. But if they intersect, they're really the same. Right? But this is not a subgroup, by the way. Yeah, this is not a subgroup. Yeah. Ignore what I said just now. This is not a subgroup. So the two whole set intersect, they have to be the same. Okay, next, what time? Okay, how about now it's 8:50. So do you have any question or not? So the punchline here is the left coset partition the group. Okay, partition. So you have a group, you take a subgroup, form all the left coset. These left coset partition the groups. Okay, so let me give you the picture. So the picture is like this. So you have a group, okay? You get your favorite subgroup, okay? And then you form your coset, okay? Form all possible, coset, okay? And then these coset will partition your group. Okay? These coset will partition. So meaning every element in your group must lie in one and only one of the coset. One and only one. The number of the partition is equal to the number of the subgroups. Wait, say again. So the number of the partition is what? Is equal to the order of G, huh? Order of the subgroup or order of the G? Order of G. Okay, so hey everyone, please look at this. So someone throw this. So you throw this statement here. So you need to verify. The number of the partition is equal to the order of G. What's the order of G? The cardinality of G. Okay. So is it true that the number of partition is equal to the order of G? Equal. So you see, now only have 4 elements here. 4 partition here. So there's only 4 elements in G. Is that what it means? No. So what does it mean? Okay, the answer is no, but we haven't get to the stage yet. So in the next stage, I will tell you what happened. But the answer is no. Okay, let's break until 9 o'clock. Okay, before that, let me take the attendance. Venus, yeah, 那天，宇泽，快乐，OK，善儿，严苛，严苛，how are you now? Better? So you skip your assignment one, is it? So make sure you do assignment two, okay? Yeah. 王泽瑞 Raylan 之余金山孙林海仁金波华英医生英奇何怡OK 雪岩呀嘉业李凯 Hey Li Kai, have you seen my team message or not? Is it what you want? Someone solve your conjecture. We can talk about it later. Yeah, someone from calculus 2 solve his project. Yuan Jia OK 本硕一定为燕博陈业林金董洁一周 OK 定宇友情真诚春宁天可轩莹莹莹莹 why you absent last Tuesday? Okay. Grace. Okay. 大业嘉文明秀 absent. Michelle behind just like Ryan Eddie Shemaine 子源 Okay. Okay. 什么？继续。 Wednesday?
Wednesday with 7.
Uh-huh.
Sunday, 7.
No, I mean, maybe we check on Monday because that's classroom. The week 7 or week 8. Week 8?
No, 8 a.m.
Oh, yeah, okay.
To go Friday. Friday. To go Friday.
Got time? Office hour? Yeah, office hour. Yeah. From 1? 1 o'clock.
1 o'clock.
1 to 2. Yeah. You coming?
Yeah, I think
Okay.
for 7 to.
Yeah, you send me a message.
Okay.
Yeah.电梯有那个电话，打那个电话。Hello, is everyone back? Please, not back yet. Alright, let's talk a bit about this first, and then we go into the real content. So why I said this is no. So if it is yes, right? This means what? Only inside this subgroup only have one element. Then here in total only have 4 elements, right? But in general, you know that subgroup might not be trivial, right? Yeah, so there might be more than one element. So there are few elements in this subgroup, and then maybe few elements in this whole set. Then you add them up. Okay. So, but the question is, can we have a control on this question, this number or not? We have a control on this number. We have a control of this number. And so the answer is this lemma here. So O left coset AH of the subgroup H of the group G actually have the same order. Okay. This statement here, right? Maybe you can see directly, but my idea should be you go and try and compute your coset of your certain group, and then you observe that they have the same order. Okay, you can try on the group that you know, but if it's infinite, then it's harder for you to check. So really, you need to check on the finite group. For example, S3, for example, S4. Okay, are the finite group. Okay, and Zn is simple. Zn is only one element in the coset, right? Just now. Verify what I say. Verify what I say. So just now we have worked it out already. So there's only one element in your coset. So 3 of these made up the cardinality of set 3. Okay. Okay. Okay, but in general, subgroup have more than one element. So we have this lemma here. So how to prove this lemma? How to show that every left coset has the same order? We just compare it to the order of subgroup. Okay, we just compare order of subgroup and the left coset. How do we compare these two? Think you got any idea? Give you a subgroup, how you get a coset? Sure. What's the homomorphism? No, this is all AH is not a group, right? So you don't need homomorphism here. Function. What's the function you need? Huh? SH equals to AH. So I have X. Let's say I have an H here. Where should this H go? The element. So you want to define a map, right? So you need to tell me where the elements go. So H have to go to where? AH. Okay. In particular, this is a multiplication by A. So maybe yeah. Multiplication by A. What's special about this morphism? Sorry, map. Yes, this is bijective. So to show something is bijective, what do you need to show? 1-to-1 or onto. Oh, there's another way to show. You need to show that this map is invertible. Okay. So to show MA is bijective, there are really two ways to show it. So there are two ways. There are two ways. There are two ways. Okay, so one way is you show that it is 1-to-1 onto. The other one is you find inverse such that this is the inverse, right? Okay, so group definition is the real inverse that you need. So MA inverse MA is the identity and MA inverse is the identity. So you need to check two. Okay, just two sides. Do you know why these two is equivalent or not? Do you know why these two are equivalent? So 1-to-1 and onto correspond to either left or right inverse. Okay, do you know which one correspond to which one? So MA, okay. So which one is left inverse, which one is right inverse? If a map is 1-to-1, okay, if a map is 1-to-1, left inverse or right inverse as is? Huh? Left inverse or right inverse as is? If this map is 1-to-1. So if you can go forward, can you go backward or not? Yes. Huh? Bijective. I mean for this map, if you go forward, if you go back to the same thing. Huh? Cannot. Huh? Cannot. Okay, how about I draw another? So this is a 1-to-1 case. Let's draw a onto case. So this is a onto case. So this is a 1-to-1 case. So which one correspond to a left inverse? Which one correspond to the right inverse? As this. I think this is the one exercise should have been done before in assignment at least. Huh? Done before or not? Done before. Okay, good. You done before. So which one? Which one is which one? Huh? Yeah. Sorry. Yeah. Okay. So left inverse means this equalities here. So if you multiply from the left to the map, you get identity. And then if you multiply from the right, get identity, you are the right inverse. This is similar to the notion of left identity and right identity. Okay. If you multiply from the left, you get identity, you are left inverse. If you multiply from the right, you get identity, you are right inverse. Okay. So I'm trying to show that these two ways are equivalent. Okay. So if you are one-to-one, left inverse exists or right inverse exists? Left inverse, right? Okay. So why? Why is it true? Okay. So let's see whether this is true or not. We argue. Okay. So we want to show that MAX is equal to identity on X, where X is in the domain. So let's fix our domain, right? So in H. Okay. Our map. Let me recall for you. Our map is from H to AH. Okay. So is this true? Okay. Let's quickly check that. So if I have an X in my H, okay, in my H, I send it across, okay, and then how do I send it back? I just follow the arrow here to send it back. But note that MA inverse is a map on the codomain. So what about these things that are not in the image of my MA? What happened to them? How do you define? You just send them to anywhere. Send them to anywhere. Send them to one of them. Okay. But your identity, you just need to check on H. Okay, you just need to check on H. As long as everything in H can get sent back to the same place, that's okay. Yeah. How about on 2? How about on 2? Let's say this is inverse as right inverse as this. What does it mean? M inverse X is equal to identity on X, where X is in H. Okay. So you have so many arrow here. You want to define an inverse. How to define? You just send to one of them. Okay, let's say you have 2 arrows going into the same element. How do you define the inverse? You just send to one of them is enough. Why? Because if you make it back by MA, you will get the same image. Okay, you start with the image here, you send it back. Either you send to here, MA will send it back again. Or you send this image back to the other pre-image, MA will send it back again. So you have identity on your object. Okay. On your object here. So here, the X here is not in H, sorry. This X is actually in the core domain here. So this is the core domain. And then this is checking on the domain. Okay? Yeah. You prove this in calculus assignment or discrete math? No. Jimbo say got it. Did you guys do this in assignment or not? Exam. Tutorial or tutorial question. Yeah. This is the standard assignment question usually in first year. Yeah. Either can appear in discrete math or calculus. Okay, this is something you have to know. Okay, so good. So which one is easier? Depend on you. So since you are learning, right, it's better for you to write down both proof. Okay. I mean to show MA is bijective. But in my now I will just show you how to find MA inverse. So what is MA inverse? It's actually just M A inverse. M inverse of A. Okay? You just multiply by A inverse instead. So if you can see that if I do MA first, okay, and then I do MA inverse, I get back my H. Right. So I need to verify. I need to verify these. I need to verify these two property here. Okay. So I have an H. I do MA, become a AH. I do MA inverse. I get a H back. Right. Because I have A inverse AH, which is H. Okay. And then how about I do MA inverse first? Okay. If I do MA inverse first, what happens? So if I start with a Y, okay, I become A inverse Y, and then I do MA, and then A inverse Y is equal to Y. So it's identity. Okay. So you see what happens here. You see, to prove that MA and MA inverse are inverses of each other, I uses the invertibility in group. Okay, invertibility of A. Okay. So the invertibility of the map becomes turned into a question of invertibility of group elements. Okay. Because you need to know that A inverse A and A inverse is the identity. If they don't hold, then this map is not invertible. Okay. So you rely on the invertibility of group element. Okay or not? Okay. So what have we established here? We know that all coset has the same elements here. Okay. So this means what? How do you change this statement here? The number of the partition is equal to the order of the group. So how you change this statement here? How do you change the statement here? What is equal to the order of the group? All elements have this. All partition have the same element, right? And then the partitions the group. So what's the total element of G? Total number of coset is the same as total number of partition, right? Okay, so how to adjust this statement here? You have to think. You see, you have a lot of group element. They are in only one of them. One and only one of them. And inside all these partitions have the same element. So in total, how many things you have? This is what? For example, let's say, okay, I give you an example. There are 5 elements in H. Okay. And then just now we proved that all the coset have the same element. Same number of elements. So in total, how many? How you calculate 30? This is exactly the idea of multiplication, right? So the order of the group is equal to the number of the partition times the order of the subgroup. Okay, so you miss out a factor is multiply by the order of H. Okay, and to be precise, let's put this as a left coset of H. Okay, yeah. You guys know how to calculate, don't know what you are calculating. Huh? Yeah. Next time when you calculate something, think a little bit more what you are doing. Okay. Okay, next. 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 Oh, I haven't defined one. Have I defined yet? Oh, okay, I haven't defined. So let's define another notion. Definition. Let H in G, okay, the number of left coset of a subgroup. Okay. So now we count the left coset of subgroup. Okay. So this is called the index of H. Okay. So when I talk about index of a subgroup, this means the number of left coset. Okay. And then we will denote it by the following. It is denoted by the square bracket G colon of H. Okay, so this is the index. So in particular, in this picture here, what's the index of H? How many left coset here? What's the number of left coset here? 4. Yeah, okay, 4. Zexuan, do you know why it's 4? What are the 4? H, AH, BH, and CH. Yeah, good. All right. Okay, good. So it follows that we have this, by the lemma, we have this theorem. A very important theorem in group theory is called the counting formula. Okay, so if you have a subgroup H, so what's the order of the group? This is what we have established just now. It's just the order of H times the index of H. Okay, so you discover this theorem just now. Okay, counting formula. Okay. The order of group is the product of order of subgroup H times the index. Okay, you can see that the idea is simple, right? Okay, just that we give it a name. Okay, we don't need to say the number of the left coset, the number of the left coset every time. Instead, we just say the index of the subgroup. Nicer or not? Okay, so this is the reason we give definition. Okay, we want to replace a idea, a big idea, squeeze into a word. Index. What is index? Number of left coset. Then what is left coset? And then you need to dig into again. Okay. So why max become very abstract? Because we keep squeezing ideas into an easier word. Squeeze a lot of idea into an easy word. So to get to know index, what you need to know? Number of left coset. You need to know what is left coset. To know what is left coset, you need to know about subgroup. Okay. To know about subgroup, you need to know about group. Okay. So why max become very complex? Because a lot of ideas got squeezed into a single word. So your job is to go into the word and then dig it out. What is the definition? What is the definition? Okay, what is it talking about? Okay, so this is typically what mathematicians do. You need to dig into what is the problem is doing about. Okay. Okay, and then next. So from here we can deduce another famous result by Lagrange. So this is the Lagrange theorem. So it means what? If you have a subgroup where G is finite, okay, G is finite means the order of the group is a finite number. Then the order of group divide the order of a subgroup divide the order of G. Okay. Okay, in particular, this is a very strong result. What do I mean by strong? What's the simple subgroup we can think of out of a group? Okay, you can get from kernel, sure. There's another one. Too trivial. let's don't do the trivial one. Yes, who said one? Who said cyclic? Good. Yeah, cyclic. What is cyclic subgroup? Cyclic subgroup means you take an element and then you keep multiplying with itself. Okay? And then you go back to identity. So the order of the cyclic subgroup is what? Let me put here our proposition. This is another. Okay, so this is a bonus. Buy one, free one. So the order of a cyclic subgroup is the order of its generator. Okay, you see, order appear in two places. One is the order of a set. The other is the order of an element. Order of a group set, you know, right? Just cardinality. Order of an element is what? The smallest integer such that, positive integer such that a to the power n is identity. Okay. So these two numbers is the same. These two numbers is the same. The claim is here. So the order of a cyclic subgroup generated is the order of A. Okay, to be precise here. Can you quickly see why or not? You take A, you generate a subgroup. Okay. And then when is it going back to identity? It's order. Let's see if we will touch this again or not. Because I remember I do something related. Because to prove this, right, it's a little bit involved, but not hard. Okay. Let me check. I think maybe we will meet this again. So maybe I don't. Or have we done this? Oh, actually we done this. I think actually we done this, but not in class, but I put in the lecture notes. Yeah, I asked you to do yourself. Okay. So this is actually equals to the order of A. Okay. You should ask a question, right? You want a subgroup generated by this A. So meaning there's an A inverse, right? For A inverse, so similarly you will have A minus 2, A to the minus 3, A to the minus 4. So where this number go? Okay. So if you see that the order of A is finite, okay, actually the inverse lies in here. The inverse lies in here. Okay, so for example, let's say A5 is equal to identity. Okay, so what's the inverse of A2? Okay, in principle, I will name it as A minus 2, right? And then I'll get A0. So what is A minus 2 here? Actually, it's just A3. So how do you get A3? You get it from A5 minus 2. Okay, so what are we doing here is actually integer modulo 5. Integer modulo 5. So in integer modulo 5, 3 is the inverse of 2. 2 is the inverse of 3. Okay. So what I'm saying is in Zn, m plus n minus m is equal to 0 mod n. Okay. N minus m is the inverse of m. Okay. Zn. Okay. If you can't recall, you should go back. I think this is what we discussed last time. Or I left you as a homework. Okay, so in particular, what you see, order of a subgroup, order of a cyclic subgroup divide the group, meaning the order of the elements divide the groups. Okay, so meaning what? If your group is a finite group, order of every element have to divide the order of the group. Okay, so meaning what? The order of the element somehow controlled by the order of the group. Okay, so if you have an element in a finite group, your element must go to 0. Okay, for some power. What is the power? That power have to divide the order of the group. So in particular, if your group, the order of your group is prime, what can the order of your element be? What number divides prime? Only 1 or prime itself. So meaning the order of the element have to be either 1 or prime. So let me write down. So let me write down first. So corollary what I said just now. So the order of an element of a finite group divides the order of the group. Okay. So another corollary. The order of elements in a cyclic group of prime order E is either 1 or P. Okay, it's either 1 or P. Because only 1 or P divides P prime. Prime is a number that only 1 or it's divided by itself. Only 1 divide P or P divide or it divided by itself. Correct? Prime numbers. Okay. Only P or 1 divided. Okay. So for example, look at the example. So let's look at Z5. Okay. So look at Z5. What are the order of 0, 1, 2, 3, 4? The order of 0 is obviously 1. Okay. So the order of 0 is 1. Order of 0. Okay, ORD. ORD of 0 is 1. How about order of 1? What's the least number you need to add to itself to get 0 here? Okay, now I want to check one by one. Venus first. Yeah, what's the order of 1? Order means what? How many times you add to itself, you get identity. Huh? You get identity. What's the identity of this group? It is 0. Okay. So how many times you have to add 1 together to get 0 mod 5? 5. Right. The least number you have is 5. How about 2? Let me ask Wita. What's the order of 2? Why? 2 plus 2 is 4. 4 is minus 1 mod 5. 4 plus 2 is 6. 6 is 1 mod 5. 6 plus 2 is 8. 8 is 3 mod 5. 8 plus 2 is 10. 10 is 5 mod 5. 5 mod 5 is 0 mod 5. Okay, 5 mod 5 is 0 mod 5. Okay. How about order of 3? Steven, what is order of 3? What is order of 3? How many times 3 have to add to itself to get 0 mod 5? 3. 3 plus 3 is what? 6. 6 is 1 mod 5. 6 plus 3 is 9. 9 is 9 plus 3, 12. 12 is 2 mod 5. 12 plus 3 is 15. 15 is 0 mod 5. So how many times? How many times? 5. So order of 3 is also 5. Okay, last one. Order of 4. Sorry. What's the order of 4? What's the definition of order? How many times the element act to itself, you get the identity. Okay, so tell me, what is 4 plus 4? 4 plus 4. What is 4 plus 4? 8. 8 is how many mod 5? 3. Okay. 8 plus 4 is what? 8 plus 4 also need to take so long. 8 plus 4. Sorry? 8 plus 4. And 8 plus 4. What is 8 plus 4? 12. Okay. 12 is how many mod 5? 2. Okay. 12 plus 4, 16. 16 is how many mod 5? 1. 16 plus 4 is 20. 20 is 0 mod 5. Okay. So you can see that all the order are the either 1 or the prime. Okay. And then this is proven using the counting formula or the Lagrange theorem. Okay. So this is not a coincidence. Okay. So this is proof. Okay, it's not a coincidence. So the order of the elements in the cyclic group of prime order P is either 1 or P. Okay. So in other words, what? In other words, what? For another corollary, there's a lot of things we can deduce from here. Okay. So suppose that my group has a group as prime order P. You just simply take any element that's not equal to identity. Okay. Then the G is really equal to the cyclic subgroup generated by A. Okay. Any one of them will generate the group. Why? For example, in Z5, last time we said that 1 generate the group, right? Okay. 2 actually also generate. 3 also generate. 4 also generate. Okay, why? So Z5 is equal to the group generated by 1, generated by 2, generated by 3, generated by 4. So why? Why? Yeah, they have the same order. They have to be the same thing because they have the same order. Order of the group is P. Order of the cyclic subgroup generated by A is also P. You have two groups with the same cardinality. So like this. So the argument is like this. Okay. For proof. So the order of A is P. Okay. The order of group is also P. But we know that A is in G. Okay. We know that A is in G. In particular, the order of A, the subgroup generated by A is a subgroup of G. So the only thing we need to show, really need to show is G is in the subgroup generated by A. G is entirely inside the subgroup generated by A. But we can argue from the cardinality. Okay, we can argue from the cardinality. So we know that the cardinality of A is n. Okay, if G is not in the subgroup generated by A, what does it mean? There's something in G that is not in A. Okay, so let's put here. So this means what? This means, let's write down what we said just now. The cardinality of, okay, so which not this means. So since A is in G, so this means the cardinality of A is less than or equal to the cardinality of G. Okay. So if it is equal, then we are done. Is it? Are we done? Almost done. Okay. But it cannot be strictly greater than. Okay, cannot be strictly greater. Okay. The cardinal of G cannot be strictly greater than A. Why? If the cardinality of G is strictly greater than the cyclic subgroup of A, means what? There exists X in G such that X is not in the cyclic subgroup. Okay. Okay. But you have one extra element, no? Right? Extra element then N. So meaning what? Meaning the cardinality of G is at least P plus 1. Right? Contradicting the cardinality of G is P. Okay. So we have to solve. Okay, so the cardinality of cyclic subgroup of A is equal to the cardinality of G. Okay. So can we deduce anything from here? We know that they have the same cardinality already. Can we deduce anything from here? I think my take will be there's some more work you need to show. There's some more things you need to do. Because you could have two sets with the same cardinality, but they are not the same. Okay. So this means what? To show this equalities subset inclusion here, you should show that for every x in G, okay, x is equal to a to the power k for some k. For some k. Positive k. Okay. So here, not enough. But what we know is they have the same cardinality. Okay. Yeah. Any question or not? Any question? Any question? Now I have 5 minutes. Either we try and finish this, maybe we don't. Okay. How about you guys want to solve this or not? Solve it? Okay. So how to do? What to do? Let's think about it. So suppose the group G has a prime order. We have a element which is not the identity, and then we want to show that G is generated by this element here. Okay. So I think this is the definition of. So what's the definition of order? So we go back to the definition of order again. What's the definition of order of an element? Okay. So suppose, okay, order of an element A, okay, for A in G is equals to P, okay, where P is prime. Meaning what? Meaning A, A2, A3, A4, and then up to A to the P, which is identity. So they are different. Why are they different? Are they different or not? They are different, right? There has to be different, right? If let's say A equals to A4, where 4 is less than B, what happened? You can reduce the order of A by cancellation law. For the sake of contradiction, if they equal at some point, then you can reduce the order. Okay, so this applies to general for I j less than P. If ij equals to ai equals to aij, this means ai minus j is actually identity. So you reduce the order. Okay, so they have to be different. So there are how many of them? There are three different elements here. Okay, so there are three different elements here. Okay, so we want to show what? We want to show that the group is actually inside the subgroup generated by A. Okay, suppose there is an element in G, okay, such that X is not in A. What does this mean? This means what? This means G with this element here, what's the cardinality? The cardinality of G is so let me put here. So what is this? So the cardinality of G is what? N, P, by definition, in the question, right? Suppose G has a prime order P, okay? And then what? Hey, you guys really are waiting for me. I have no extra G is not in A. Huh? Why? Why P plus 1? Huh? For one more element. Why? Okay. Wait. Sorry. Let's come back again. So you see. So the element of come back again. Okay, let's step back again. So we know that the cardinality of G union X is still P. It's still P, right? Because X is in G, it's still P. But what happened? There's one guy is not in A. Okay, this one guy is not in A. I think is it getting abstract or not? How about give you a number to think about it? So let's say we work with P equals to 3. Okay, so our G is here, our A is here. Okay, I have 3 things in G, 3 things in A. Okay, let's say what we have shown. What have we shown? Okay, this one no use already. So we know that. We also know. We know the cyclic subgroup generated by A is a subset of G. Okay, meaning what? We know that all elements here is inside here. Okay, so maybe I use a different color. Okay, I use different color. So maybe I use a red one. Okay, so we know that the red guy are here. Okay. But let's say there's one guy of G. Okay, so there was one guy of G is in G, but not in here. Is there a contradiction or not? Is there a contradiction? Any contradiction or not? So this is what we know. Okay, we want to show the other direction. Okay, suppose there's one guy, okay, is not in A. What's the contradiction? Any contradiction? So meaning what? Meaning some of the red dot have to be the same. Meaning some of the red dot have to be the same. Okay? Meaning some of the red dots need to be the same. Then AI equal to sum AJ. Because this red dot doesn't match to all of this. So some red dot must be equal. Okay, meaning AI equals to AJ for some IJ less than P. But from the discussion just now, what will happen? What will happen? We will get a number which is smaller than P, but A to the where I minus J is less than P. Can this happen or not? Cannot, because P is the smallest number for A to go to infinity. Okay. So actually we are contradicting the order of A. Okay. Because it's a smaller number than P that it goes to infinity. Okay. Does it make sense or not? Okay, so first we divide into two. We look at two things. Let me quickly recap what I discussed just now. We have two things. We have a group G. We have a group A. Okay, a group generated by cyclic subgroup generated by A. Let's say we fix our P as 3. Okay. So what we know is the cyclic subgroup is always a subgroup in G. Okay. Because group is closed. Okay. So meaning we can find these 3 elements in my group. Okay. So the other direction is to show that G is a subgroup of the cyclic subgroup. So let's say it is not. What does it mean by it's not a subgroup? Meaning you can find something in G which is not in A. Okay, you can find something in G which is not in the cyclic subgroup generated by A. This means what? This means there's one guy here is not in my subgroup. But just now you said you already have 3 guys from the cyclic subgroup inside here. So meaning what? Meaning 2 of them must be equal. Okay, 2 of them must be equal. Okay, if 2 of them must be equal, that means what? That means there exists some I and J where I is not equal to J and less than P, that AI equals to AJ. Okay, and then we just take the difference, depending which one is greater. Okay, so maybe I put like this: A greater than J, and then all of them are less than P. Okay. Then what we deduce? We deduce that A actually to the I minus J is the identity. But we say that P is the least order. Only up to P, A can go back to identity. You cannot go to identity before P. Okay, but this is the contradiction. Okay. Because I minus J must be less than P. Okay. Okay, any question before we take a break? Yeah. A bit many. Yeah, so, yeah, okay. Slowly, you will get used to it. Okay. But for now, what you have to convince yourself is every step is linked. Okay, you cannot get the big picture is okay, but at least every step must be linked. Locally is linked. Okay, you cannot get the big picture is okay, but you need to make sure every step is linked logically. Okay, locally have to be true, and then you question out globally. You mean assignment? Sure, definitely. Everything proven is in lecture you can use unless I ask you to prove back the same thing, then you can use. Okay. If I ask you to prove that statement that is shown, then you need to prove that. Okay. You cannot say by lecture note this is proven. No. Okay. Yeah. You can use it. Okay. But if I ask you to prove it, then you have to prove it. Okay. Okay. See you next week. So I have an office hour today and Friday. If you want to come, you can message me first.